What if black holes came first? Not after stars, not after galaxies, before everything. Webb pointed its golden mirrors at the edge of time and found monsters waiting there. Black holes so massive, so ancient, so impossible that scientists cannot explain them. 300 million times heavier than our star. Fully grown when the universe was still a baby. The old theories are broken. The math does not work. The timeline makes no sense. Something created these giants before creation itself was finished. This is the story of what Webb found in the dark. Deep in the oldest corners of the universe, something is very wrong. The James Webb Space Telescope has been staring into the past, capturing light that traveled for over 13 billion years to reach its golden mirrors. What it found has left scientists scrambling for answers. Supermassive black holes, everywhere, far too many of them, far too early in cosmic history. These are not small objects. We are talking about gravity wells containing the mass of millions of stars crushed into a single point. They sit at the centers of galaxies, bending space and time itself around their enormous weight. Nothing escapes them, not light, not matter, not even information about what falls inside. Here is where it gets strange. These monsters appeared less than 1 billion years after the Big Bang. Some showed up just 500 million years into cosmic history. That might sound like plenty of time. But in the life of a universe that has existed for nearly 14 billion years, it is barely a blink, a cosmic eye blink in which the largest structures somehow already existed. Scientists have confirmed the standard explanation requires patience. A massive star must first be born from collapsing gas clouds. It must burn through its nuclear fuel over millions of years. Then it must explode in a violent supernova and collapse into a black hole. After that, the black hole must find other black holes, merge with them, and slowly grow larger by eating gas and dust from its surroundings. This process works. We have observed it happening in the nearby universe. But it takes billions of years to build something truly massive. So when Webb pointed its instruments at the earliest galaxies and found fully grown supermassive black holes already sitting there, astronomers knew something was missing from the story. The universe simply did not have enough time for these beasts to grow the traditional way. One researcher described it like finding a skyscraper in a neighborhood where construction started yesterday. The building exists, you can walk inside it, but the timeline makes absolutely no sense. And it gets worse. These ancient black holes are far too big compared to their host galaxies. In the modern universe, a supermassive black hole typically contains about 0.5% of its galaxy's total mass. The galaxy outweighs its central black hole by a factor of 200 or more. But in the early universe, Webb found black holes weighing 10% of their host galaxies. Some contain nearly half the mass of all the stars around them combined. The entire relationship is completely flipped from what we expected. This means one of two things. Either these black holes grew impossibly fast, somehow breaking the known laws of physics, or they started out already massive, forming through some process we never anticipated and barely understand. This discovery matters for humanity. If we misunderstand how the largest structures in the universe formed, we misunderstand everything about cosmic evolution, including how galaxies like our own Milky Way came to exist, including how we came to exist. Scientists have debated these possibilities for years, but Webb changed everything. Before this telescope, we could only guess what the early universe looked like. Now we have actual pictures, and those pictures are forcing us to rewrite the fundamental rules of cosmic evolution. But what if the very idea of how black holes are born is completely wrong? The answer lies in something far stranger than anyone imagined. Before we go deeper into this mystery, you need to understand exactly what we are dealing with here. A black hole sounds simple enough when you first hear about it. It is a region of space where gravity has become so incredibly strong that nothing can escape its pull. Not matter, not radiation, not even light itself, which is the fastest thing in the universe. Once something crosses the boundary called the event horizon, it is gone forever, trapped for eternity. But supermassive black holes are a completely different breed of monster. While a regular black hole formed from a collapsed star might contain 5 to 50 times the mass of our star, a supermassive black hole holds millions to billions of times that amount. The difference in scale is almost impossible to comprehend. It is like comparing a single grain of sand to an entire mountain range. Picture this to understand the scale. Take our entire solar system, every planet from Mercury to Neptune, every moon orbiting those planets, every asteroid tumbling through the darkness, every comet, every grain of dust floating between worlds. Now multiply all of that mass by 4 million, then crush it down into a space smaller than the distance between our star and the nearest neighboring star system. That is roughly what sits at the center of our own Milky Way galaxy right now. Scientists have confirmed this object exists through decades of careful observations. We call it Sagittarius A star. It lurks about 26,000 light-years from Earth, surrounded by stars that whip around it at several percent the speed of light. The only thing that could possibly make stars move that fast is an incredible concentration of mass hidden in an impossibly small space. Here is what should genuinely terrify you about these objects. Sagittarius, a star, is actually modest compared to the true giants out there. The supermassive black hole sitting at the center of a galaxy called Messier 87 contains 6.5 billion stellar masses. Its event horizon, the point of no return, stretches wider than our entire solar system from edge to edge. You could drop our whole cosmic neighborhood inside, and it would vanish without a trace. These objects do not sit quietly in space doing nothing. As gas and dust fall toward a supermassive black hole, the material forms a spinning disk heated to millions of degrees by friction and compression. This disk glows so brilliantly that it can outshine the entire galaxy surrounding it. Hundreds of billions of stars outshone by one feeding black hole. When a supermassive black hole feeds actively like this, we call the whole system a quasar. These cosmic beacons are visible from billions of light years away, their light cutting through the darkness of intergalactic space. But here is what makes them truly strange and deeply unsettling. Despite all this power and all this mass, a supermassive black hole is technically just empty space. There is no surface to land on, no solid core hiding inside. Just a boundary in space-time where escape becomes forever impossible. The matter that created it has been crushed down to something our physics cannot fully describe or even imagine. What we know for certain is this: nearly every large galaxy in the universe contains one of these monsters at its heart. They seem absolutely essential to how galaxies form and evolve over cosmic time. And that deep connection between black holes and galaxies is exactly why Webb's discoveries disturb scientists so much. If black holes came first, everything we thought about cosmic evolution might be running completely backwards. For decades, scientists believed they completely understood how black holes come into existence. The story begins with the most massive stars scattered across the universe. A star is essentially a controlled explosion happening continuously for millions or billions of years. Gravity tries relentlessly to crush the star down into nothing. Nuclear fusion in the core pushes back with equal force, generating enough energy to hold the star up against its own tremendous weight. As long as the star has fuel to burn, this delicate balance holds steady. But massive stars burn through their fuel far more quickly than smaller ones. A star 20 times heavier than ours might completely exhaust its hydrogen supply in just a few million years. That sounds like a long time by human standards. But compared to our star, which will burn for 10 billion years, these giants live fast and die young. When the fuel finally runs out, disaster follows immediately. Without fusion pushing outward from the core, gravity wins the battle instantly. The core collapses inward at roughly a quarter of the speed of light. The outer layers of the star come crashing down, slam into the collapsing core, bounce off with tremendous violence, and explode outward in a supernova. For a few weeks, this single dying star can outshine an entire galaxy containing hundreds of billions of living stars. This is confirmed science. We have observed supernovae happening across the universe. We understand the physics deeply. What remains after the explosion depends entirely on how massive the original star was. If the leftover core weighs below about 3 stellar masses, it becomes a neutron star. These objects are incredibly dense, but ultimately stable. A single teaspoon of neutron star material would weigh about 6 billion tons if you brought it to Earth, the mass of a mountain compressed into a sugar cube. But if the core exceeds that critical limit, absolutely nothing can stop the collapse from continuing forever. Not the pressure of electrons pushing against each other, not the pressure of neutrons packed impossibly tight. Gravity simply overwhelms every force in nature. Matter falls inward without end. A black hole is born from the corpse of a star. This is called a stellar mass black hole. They typically range from about 5 to several dozen stellar masses. We have detected many of them through gravitational wave observatories, which can sense the ripples in space-time created when two black holes spiral together and merge in a cataclysmic collision. Here is where the traditional theory attempts to explain supermassive black holes. Scientists believed these giants simply grow from smaller stellar seeds over immense timescales. A stellar mass black hole forms in a dense region of a young galaxy. It begins eating gas from its surroundings. Occasionally, it merges with another black hole. Over billions of years, it slowly accumulates mass through this patient process. This explanation is called the light seed model. You start with something small, maybe 10 to 100 stellar masses, and you let it grow through cosmic time. The math actually works for black holes in the modern universe. Given 13 billion years of eating and merging, a small black hole could theoretically grow into a supermassive giant. But here is the problem that now keeps scientists awake at night. Webb found supermassive black holes existing when the universe was only 500 million years old. The light seed model simply cannot explain them. There was not enough time for this slow growth. The first stars had barely formed before these giants appeared. Something else must have happened in the early universe, something that created massive black holes almost instantly. The numbers tell a brutal and unavoidable story. Let us walk through exactly why the traditional formation model completely fails to explain what Webb discovered. The universe began 13.8 billion years ago with the Big Bang. For the first few 100,000 years after that initial explosion, everything was far too hot for even simple atoms to form. Space was filled with a glowing fog of charged particles called plasma. No stars existed, no galaxies existed, just expanding energy slowly cooling in the endless void. Around 380,000 years after the Big Bang, the universe finally cooled enough for hydrogen atoms to form and hold together. The glowing fog faded and space became transparent. But now, the cosmos was completely dark. No sources of light existed anywhere. This period is called the Cosmic Dark Ages. Scientists have confirmed through multiple independent observations that it lasted roughly 150 million years, an eternity of pure darkness across the entire universe. Then the first stars finally ignited and broke the darkness. These primordial giants, called population 3 stars, were completely unlike anything existing today. Made of pure hydrogen and helium with absolutely no heavier elements, they burned extremely hot and died extremely fast. Some may have reached several hundred stellar masses, far larger than any star we see now. When these first stars exploded in supernovae, they left behind the first stellar black holes in cosmic history. But even the most massive population 3 star would only create a black hole of perhaps 100 stellar masses at the absolute maximum. Now, here is the mathematical challenge that completely breaks the standard model. A black hole observed just 500 million years after the Big Bang needs to have already reached 100 million to 1 billion stellar masses. That means starting from a seed of 100 stellar masses and somehow growing by a factor of 1 million to 10 million in that short time. Can a black hole possibly eat that fast? Can it grow that quickly? The answer, confirmed by fundamental physics, is absolutely not. There exists a speed limit for how quickly any black hole can consume surrounding material. It is called the Eddington limit. When a black hole feeds on gas, that material heats up dramatically and radiates intense energy outward. That radiation creates pressure pushing against incoming gas. At a certain feeding rate, the outward pressure perfectly balances the inward pull of gravity. The black hole physically cannot eat any faster no matter how much food surrounds it. At this maximum limit, a black hole roughly doubles its mass every 45 million years. Starting from a seed of 100 stellar masses, reaching 100 million stellar masses would require about 800 million years of continuous feeding at the absolute maximum possible rate, never slowing down, never stopping. But the universe was only 500 million years old when these black holes were observed. The math simply does not work. This is not speculation or theory. This is confirmed physics applied directly to confirmed observations. The numbers cannot be made to fit, no matter how creative the calculations. The conclusion becomes completely unavoidable. Either our understanding of black hole growth is fundamentally and deeply wrong, or these supermassive black holes did not grow from stellar remnants at all. They must have been born already massive, through some completely different process. And if that is actually true, humanity's entire picture of how the cosmos assembled itself needs to be completely rewritten from the beginning. Before we explore the alternative theories that might solve this puzzle, you need to understand exactly why black holes have a maximum eating speed. This fundamental limit explains why the early monsters are so completely impossible under standard physics. Picture a black hole floating in space, surrounded by a vast cloud of gas. Gravity reaches out and pulls that gas inward toward the event horizon. As individual particles fall toward the black hole, they accelerate to tremendous speeds. They collide violently with other particles also falling inward. Friction converts all that motion into intense heat. The gas reaches temperatures of millions of degrees as it spirals closer. Hot gas radiates energy. It glows brilliantly in X-rays and ultraviolet light, releasing photons in every direction. This radiation streams outward from the black hole's vicinity, pushing against incoming gas like a powerful fan pushing against falling leaves. The light itself creates pressure working against gravity. At low feeding rates, this radiation pressure remains relatively weak. Gas falls inward easily, without much resistance. The black hole gains mass at a steady pace, but as the feeding rate increases, so does the radiation blasting outward. At some critical point, the outward pressure exactly balances the inward pull of gravity. Gas trying to fall in gets pushed back by energy released from gas that already fell in. The black hole creates its own barrier to further growth. This balance point is called the Eddington limit, named after the physicist Arthur Eddington, who first calculated it roughly a century ago. Scientists have confirmed this limit exists through observations of actively feeding black holes throughout the universe. It is not theoretical, it is measured reality. The exact limit depends on the mass of the black hole involved. Heavier black holes have stronger gravity, so they can pull harder against the radiation pressure. But heavier black holes also produce more intense radiation when they feed on surrounding gas. These two effects roughly cancel each other out, giving every black hole a similar fractional growth rate relative to its current size. At the Eddington limit, a black hole increases its mass by approximately 1% every million years. That might sound impressively fast until you actually calculate how much total growth the early universe black holes somehow achieved. Starting from a seed of 100 stellar masses, reaching 100 million stellar masses requires a million-fold increase in size. At 1% growth per million years, achieving that multiplication takes roughly 700 million years of absolutely continuous maximum rate feeding, never pausing, never slowing, never running short of gas to consume. The universe was only 500 million years old when some of these black holes were already observed by Webb. Here is why this impossible math matters for understanding our place in the cosmos. Some researchers desperately proposed ways to temporarily exceed the Eddington limit. Maybe gas flows inward through narrow channels that somehow avoid the radiation pressure. Maybe feeding happens in brief, intense bursts rather than continuously. But even these optimistic scenarios cannot explain the most extreme cases Webb discovered. And there is another serious problem with pushing the limits. Feeding at such tremendous rates would produce absolutely enormous amounts of radiation blasting outward. That radiation would heat all surrounding gas to extreme temperatures and blow it completely away from the galaxy. The black hole would literally destroy its own food supply. The Eddington limit is not merely a speed limit. It represents a fundamental constraint built into the laws of physics governing how gravitational systems can grow. Unless these black holes somehow started out already massive through some completely different and unexpected process, that process might have happened in the very first seconds of existence itself. When the James Webb Space Telescope began its deep surveys of the ancient universe, astronomers expected to find young galaxies in their earliest stages of formation. They expected to see stars being born inside collapsing gas clouds. They expected to witness the gradual assembly of cosmic structure building up slowly over billions of years. What they absolutely did not expect were the little red dots. Scattered across Webb's deepest images of the cosmos, these mysterious objects appeared as tiny points of reddish light against the black background of space. At first, nobody had any idea what they actually were. They were far too compact to be normal galaxies. They were far too bright to be individual stars at such extreme distances. They were far too red to match any known type of astronomical object at those distances. The redness comes partly from their extreme distance from Earth. Light from these objects has traveled so incredibly far that the expansion of the universe itself stretched the wavelengths during the journey. Blue light became red light. Visible light became invisible infrared radiation. The farther away an object sits, the more its light gets stretched toward the red end of the spectrum. But distance alone could not explain their unusual compactness or their surprising brightness. Something truly unusual was happening inside these little red dots, something that demanded explanation. And what scientists eventually found changed everything we thought we knew about the early universe. Over the past 2 years, astronomers have carefully studied dozens of these objects using Webb's powerful spectroscopic instruments. They split the incoming light into its component wavelengths, like a prism splitting sunlight into a rainbow. They searched for specific chemical signatures that would reveal what these mysterious objects actually contained deep inside. The answer shocked the entire scientific community when it finally emerged from the data. Many of these little red dots contain actively feeding supermassive black holes at their centers. The extreme redness comes from thick cocoons of gas and dust completely surrounding the black holes. These dense cocoons absorb shorter wavelengths of light and then re-emit that captured energy as infrared radiation that Webb can detect. Inside each cocoon, a supermassive black hole is devouring material at tremendous rates. Gas spirals inward toward the event horizon, heats up to extreme temperatures, and glows brilliantly with the energy of billions of stars. But the surrounding dust shroud blocks most of that intense light from escaping directly into space. Only the longest wavelengths manage to leak through the cocoon and reach our telescopes. One research team described these objects as young black holes wrapped in cosmic blankets, still growing rapidly inside their primordial nurseries, hidden monsters feeding in the dark. Scientists have confirmed this interpretation through detailed spectroscopic analysis. They can actually see the distinct chemical fingerprints of actively feeding black holes embedded in the data. The evidence is now overwhelming. These objects exist at distances corresponding to just 500 million to 1 billion years after the Big Bang. This is precisely the era when supermassive black holes should not have had enough time to form through any traditional channel involving stellar evolution and gradual growth. Yet here they are, dozens already confirmed with certainty, possibly hundreds more waiting in the data, maybe thousands lurking in deeper surveys that have not yet been fully analyzed. Their sheer abundance strongly suggests that whatever process created them was not rare or unusual. It was not some cosmic fluke requiring extraordinary circumstances. It was something that happened commonly across the entire early universe, producing supermassive black holes in young galaxies everywhere astronomers look. But what exactly was that mysterious process? The little red dots themselves hold tantalizing clues that point towards something scientists never seriously expected. And those clues lead us to question whether stars were ever truly needed at all for creating the universe's largest black holes. The James Webb Space Telescope, launched in late 2021 aboard a European Ariane rocket and began its science operations in mid-2022. Within just a few months of opening its eyes to the universe, it started completely rewriting astronomy textbooks that had stood for decades. Webb carries a primary mirror 6.5 meters wide, assembled from 18 individual hexagonal segments, all coated in a thin layer of pure gold. This enormous mirror collects extremely faint infrared light traveling from the farthest reaches of the observable universe, light that left its sources billions of years ago and has been journeying through expanding space ever since. Because light takes time to cross the vast distances of the cosmos. Looking at extremely distant objects literally means looking backward through time itself. An object sitting 1 billion light years away appears to us exactly as it was 1 billion years ago when that light first began its journey. Webb can see objects so incredibly distant that their light has been traveling for over 13 billion years, almost as long as the universe itself has existed. We are seeing the baby pictures of creation. Before Webb launched, the Hubble Space Telescope was humanity's best tool for studying the distant universe. But Hubble observed primarily in visible and ultraviolet wavelengths of light. Here is the critical problem that limited Hubble. Light from the earliest galaxies gets dramatically stretched into the infrared part of the spectrum by cosmic expansion during its long journey. This stretching made those ancient objects completely invisible to Hubble's cameras no matter how long it stared. Webb was specifically designed and built to see exactly what Hubble could never detect. The results have been genuinely shocking to astronomers worldwide, and they have been confirmed repeatedly through multiple independent analyses by different research teams using different methods. Webb found galaxies that formed much faster than any theoretical model predicted. It found galaxies that grew much larger than expected in the available time. It found galaxies containing far more stars than the physics of early star formation should have allowed. And it found supermassive black holes that were far too massive to fit within any existing model of cosmic evolution. One particularly striking discovery came from a distant galaxy containing an actively growing black hole with mass around 100 million times that of our star. The galaxy surrounding this monster contains far fewer stars than it should based on the mass of its central black hole. The expected relationship is completely inverted. Normally, astronomers observe that a black hole grows in lockstep alongside its host galaxy. The two should maintain a certain predictable mass ratio throughout cosmic history. But in this ancient galaxy, the black hole is dramatically overmassive. It somehow grew much faster than the surrounding stars could possibly form. Another remarkable discovery involved a galaxy observed just 470 million years after the Big Bang. This galaxy contains a supermassive black hole that accounts for an enormous fraction of the system's total mass. Researchers concluded it most likely formed through direct collapse of primordial gas rather than through any process involving stellar evolution. Then came an object that defied absolutely everything astronomers thought they understood. A naked black hole. A supermassive giant floating through space with almost no surrounding galaxy visible at all, weighing approximately 50 million stellar masses. Existing completely alone in the early universe without the expected cocoon of stars, this directly contradicts every theoretical model requiring black holes to grow up inside galaxies alongside stellar populations. These discoveries are not isolated anomalies or measurement errors. They represent a clear and undeniable pattern emerging from the data. The early universe contained supermassive black holes that simply should not exist according to any traditional theory of cosmic evolution. Something else entirely was happening back then, something that fundamentally changes what we understand about our own cosmic origins. For decades, while mainstream astronomy focused on the standard model of black hole formation, a small handful of theoretical physicists quietly proposed a radically different pathway to creating supermassive black holes. Instead of starting microscopically small and growing over billions of years through patient feeding and mergers, what if some black holes simply formed already massive from the very beginning? The idea is called direct collapse. Under very specific and unusual conditions, a vast cloud of primordial gas could potentially skip the entire star formation phase and collapse straight into a black hole without any intermediate steps. This theory was considered fringe science for many years. Most astronomers dismissed it as theoretically interesting but probably irrelevant to the real universe. Now, Webb is providing compelling evidence that direct collapse actually happened on a massive scale throughout the early cosmos. Here is how the process might actually work in practice. In the early universe, enormous clouds of hydrogen and helium gas filled the dark void between forming structures. Normally, when such a cloud begins collapsing inward under the pull of its own gravity, something important happens that prevents direct black hole formation. The gas heats up as it compresses. That heat creates outward pressure, pushing back against the inward pull of gravity. Eventually, this pressure causes the cloud to fragment into many smaller pieces. Each fragment then continues collapsing independently until it becomes a star. Stars then live out their lives over millions of years, burn through their nuclear fuel, and eventually die in explosions or quiet fades. Only after this entire long stellar life cycle completes do black holes finally form from the remnants. The process requires patience measured in millions of years at minimum. But what if a particular gas cloud somehow never fragmented into smaller pieces? What if it stayed whole and kept collapsing as a single unified mass until it became a black hole directly without ever forming any stars along the way? For this remarkable outcome to occur, the gas must somehow avoid cooling down during the collapse. Cold gas fragments easily into star-forming clumps because it lacks the pressure to resist gravity's squeeze. Hot gas stays together as a single mass because the heat provides enough outward pressure to keep the cloud unified. If something keeps the gas warm throughout the entire collapse process, it might fall inward as one single massive object, rather than breaking apart into countless stellar mass pieces. Several different mechanisms could potentially provide this crucial heating effect. Intense ultraviolet radiation flooding in from nearby young galaxies could prevent the gas from cooling efficiently. Violent turbulence generated by cosmic collisions could continuously inject energy throughout the cloud. Strong magnetic fields, threading through the gas, could suppress the fragmentation process through complex electromagnetic effects. If these conditions align correctly, the entire massive cloud collapses into what scientists call a supermassive star. This extraordinary object might contain anywhere from 10,000 to 100,000 stellar masses in a single bloated structure. It burns at extreme temperatures and dies extremely fast by cosmic standards, perhaps lasting only a few 100,000 years before exhausting itself. When this supermassive star finally dies, it does not explode outward like a normal supernova scattering material across space. Instead, it collapses completely inward into a black hole, retaining most of its enormous mass in the process. A single dramatic event creates a black hole seed containing tens of thousands of stellar masses instantly. This is called the heavy seed model. Instead of starting with a tiny 10 stellar mass black hole and somehow growing it by a factor of 10 million over insufficient time, you start with a seed of 50,000 stellar masses and only need to grow it by a factor of 1,000. Suddenly, the math actually works within the available cosmic time. The timeline becomes manageable. The previously impossible becomes entirely possible. For many years, direct collapse remained purely theoretical, with no observational support. Then Webb started finding objects that matched the theoretical predictions with remarkable precision. The conditions required for direct collapse are genuinely extreme but entirely achievable under the right circumstances. Scientists have now identified several realistic scenarios where massive primordial gas clouds might have collapsed directly into black holes without ever forming stars along the way. The single most important requirement is keeping the gas hot throughout the entire collapse process. This principle has been confirmed through sophisticated computer simulations that model the detailed physics of collapsing gas clouds in the early universe. Hydrogen gas naturally radiates away its internal heat through molecular transitions. Here is how this cooling process works at the atomic level. Hydrogen molecules vibrate and rotate when they contain thermal energy. These vibrations and rotations release infrared photons that carry energy away from the gas cloud into empty space. This steady cooling allows the gas to compress further, lose more heat, compress even more, and eventually fragment into many small, dense clumps that each become individual stars. To enable direct collapse, instead of star formation, something must prevent hydrogen molecules from forming in the first place, or destroy them as fast as they appear. Without these molecular refrigerators operating, the gas simply cannot cool efficiently. It stays hot, maintains high internal pressure, stays smooth and unified, and collapses as a single coherent mass rather than fragmenting into countless stellar seeds. The key mechanism is intense ultraviolet radiation bathing the gas cloud from outside. Powerful ultraviolet light splits hydrogen molecules apart through a process called photodissociation, faster than new molecules can form through random collisions. If a collapsing gas cloud happens to sit near a young galaxy that pumps out enormous amounts of ultraviolet radiation from its hot young stars, that radiation can effectively sterilize the entire cloud. No molecular cooling means no fragmentation. No fragmentation means direct collapse becomes possible. This creates a very specific environment where direct collapse can actually occur. You need an extremely massive gas cloud located close enough to a strong ultraviolet source to stay completely molecule-free throughout its collapse. But the cloud cannot sit too close to that radiation source, or the intense light will blow the gas apart entirely before it can collapse. Scientists sometimes call this the Goldilocks zone for primordial black hole formation. Not too far from radiation, not too close, just right for creating monsters. Computer simulations demonstrate that this scenario is rare but entirely plausible given the conditions of the early universe. In the dense and chaotic environment shortly after the Big Bang, such configurations would have naturally occurred through random chance. Perhaps roughly 1 in every 1,000 massive gas clouds experienced exactly the right conditions for direct collapse to proceed. There are other pathways to direct collapse beyond ultraviolet sterilization. Atomic cooling halos represent regions where gas can cool through atomic transitions rather than molecular ones. Atomic cooling operates at significantly higher temperatures and leads to much faster collapse rates. Under certain specific conditions, gas falls inward so rapidly that it physically cannot fragment before reaching the extreme densities required for black hole formation. The collapse simply outruns the fragmentation process. Colliding gas flows provide yet another route to direct collapse. When two massive streams of primordial gas collide at tremendous speeds in the early universe, the resulting violent turbulence heats the combined material intensely and prevents fragmentation through continuous energy injection. The merged gas mass then collapses coherently as a single object. All three pathways ultimately lead to remarkably similar outcomes despite their different mechanisms. A primordial gas cloud containing perhaps 1 million stellar masses collapses into a supermassive star of roughly 100,000 stellar masses. This bloated giant almost immediately collapses further into a black hole of similar mass, without any intervening stellar evolution. This seed is already enormous compared to anything stellar collapse could produce. It does not need to merge with thousands of other black holes over billions of years. It does not need to feed at physically impossible rates for hundreds of millions of years straight. It just needs to grow by a factor of 1,000 over the next few hundred million years, well within the bounds of normal physics and the Eddington limit. The theory predicted specific observational signatures that astronomers should find if direct collapse actually occurred over massive black holes sitting in undersized galaxies, black holes that formed before their host galaxies fully matured. Webb found all of these predicted signatures, and something even stranger might explain the very first seeds of all cosmic structure. Direct collapse from gas clouds represents one alternative pathway to creating massive black holes quickly, but an even more exotic possibility reaches all the way back to the very first moments of existence itself. A time before atoms, before light, before anything we would recognize as matter. Primordial black holes are hypothetical objects that formed not from collapsing stars or cooling gas clouds, but directly from density fluctuations in the infant universe itself. Within the first second after the Big Bang, before the cosmos was even 1 minute old, this remarkable theory suggests that some black holes have existed since before atoms formed, before the first stars ignited, before anything resembling normal matter existed anywhere in the universe. They would be older than everything else we can see or measure. The concept dates back to 1971, when the brilliant physicist Stephen Hawking, working alongside Bernard Carr, first worked out the detailed theoretical framework for how such objects could form. During the earliest moments after the Big Bang, the entire universe was extraordinarily hot and extraordinarily dense beyond anything we can truly imagine. Tiny quantum fluctuations in this primordial soup could have been dramatically amplified by gravity, creating small pockets dense enough to collapse directly into black holes without requiring any other process. These primordial black holes would have formed before any stars existed anywhere, before any atoms existed anywhere, before the fundamental forces of nature even settled into their current familiar forms. They represent a completely different category of object, requiring no stellar precursor whatsoever. The mass of any primordial black hole would depend entirely on exactly when during the early universe it happened to form. Black holes that formed earlier, when the universe was even denser and hotter, would end up smaller in mass. Those that formed slightly later, when densities had dropped somewhat, could be much larger. The possible range spans an enormous spectrum from microscopic objects far smaller than atoms all the way up to giants containing thousands of stellar masses. Hawking later showed through elegant mathematics that the very smallest primordial black holes would have completely evaporated by now through quantum effects he discovered called Hawking radiation. But larger primordial black holes would survive easily to the present day, lurking invisibly throughout the cosmos. For decades, after Hawking's original papers, primordial black holes remained purely theoretical speculation without any observational evidence supporting their actual existence. The scientific community largely set this fascinating idea aside as an intellectual curiosity probably irrelevant to explaining the real universe we observe. Then Webb started discovering supermassive black holes in the earliest observable epoch of cosmic history, objects that simply could not exist under standard formation theories. And suddenly, primordial black holes became a serious scientific explanation once again. If primordial black holes actually formed with masses of thousands or even tens of thousands of stellar masses during that first second of existence, they would have provided perfect ready-made seeds for supermassive black hole growth. No waiting around for the first stars to form and die. No requiring special gas cloud conditions that might be rare. The seeds were simply created at the very beginning of time itself and scattered throughout the universe. This scenario neatly explains the otherwise impossible timing problem that Webb revealed. Primordial black holes would have existed before anything else in the entire universe. They would have had a massive head start of hundreds of millions of years compared to any formation pathway requiring stellar evolution first. They were already there, waiting, when galaxies began assembling around them. Some scientists now seriously theorize that these ancient objects might also constitute the mysterious dark matter that outweighs ordinary visible matter in the universe by a ratio of 6:1. If true, the implications for our understanding of the cosmos would be absolutely revolutionary across multiple fields of physics. The evidence supporting primordial black holes continues to accumulate with every new observation. The possibility that black holes were among the very first structures to exist anywhere in the universe is now taken seriously by mainstream science, and the discoveries supporting this radical idea have only accelerated in recent years. In late 2023, astronomers announced a discovery that sent genuine shockwaves rippling through the entire scientific community. They had found an ancient galaxy containing something that simply should not exist according to everything we thought we understood about cosmic evolution. This particular galaxy sits at such an extreme distance that we observe it as it appeared just 470 million years after the Big Bang. The universe had barely reached 3% of its current age. Cosmic structures were still in their earliest infancy. The first generation of stars had only recently begun illuminating the darkness. Galaxies were mere embryos compared to the mature spirals and ellipticals we see nearby today. Yet deep inside this tiny ancient galaxy lurked a fully formed supermassive black hole already actively feeding on surrounding gas. The discovery required two of humanity's most powerful space telescopes working together in careful coordination. Webb detected the distant galaxy using its sensitive infrared cameras, revealing the faint glow of ancient starlight stretched red by cosmic expansion. Simultaneously, the Chandra X-ray Observatory detected high-energy radiation emanating from exactly the same cosmic location. This X-ray signature represents the telltale fingerprint of an actively feeding black hole. X-rays in astronomy come from the innermost regions of accretion disks, where temperatures reach millions of degrees through extreme friction and compression. Only a truly massive black hole pulling in material at tremendous rates could possibly produce the intense X-ray signature that Chandra detected from this incredible distance. By carefully combining data from both telescopes and accounting for all uncertainties, researchers estimated the central black hole mass at somewhere between 10 million and 100 million stellar masses. The uncertainty range is large because measuring black hole masses across such vast cosmic distances pushes our instruments to their absolute limits. Here is where this discovery becomes truly disturbing and impossible to explain through traditional models. The host galaxy itself is remarkably small for harboring such a monster. It contains perhaps only a few 100 million stellar masses worth of stars based on the observed brightness. In the local universe that we can study in detail, a galaxy this small and modest would typically host a central black hole of maybe 100,000 stellar masses at most, usually even less. This ancient black hole appears at least 100 times more massive than it has any right to be given its tiny host galaxy. This is not some subtle statistical discrepancy, requiring careful analysis to detect. The black hole contains roughly as much mass as fully half of all the stars in its entire host galaxy combined. The expected ratio between black hole and galaxy mass is completely inverted from what we observe everywhere in the modern universe. A theoretical astrophysicist named Priyamvada Natarajan, working at Yale University, had actually predicted exactly this kind of bizarre object over a decade before Webb launched. Her detailed mathematical models of direct collapse black holes suggested they would naturally create what she termed overmassive black hole galaxies, systems where the central black hole rivals or even exceeds the total stellar mass surrounding it. When this ancient galaxy was finally discovered and characterized, it matched her theoretical predictions with remarkable and almost eerie precision. The mass ratio fit her models. The cosmic timing fit her models. The properties of the surrounding stellar population fit her models. Everything aligned perfectly with the direct collapse scenario she had championed for years, while most astronomers remained skeptical. This represented the first strong observational evidence that heavy seeds actually formed in the real early universe rather than just in theoretical calculations. The mathematical predictions and actual observations finally matched each other. And this galaxy was just the beginning of the revolution. More overmassive black holes kept appearing in Webb data with every new observation. But the strangest discovery still lay ahead. A black hole floating almost completely alone in the cosmic void. If the previous discovery was surprising and difficult to explain, this next one was downright bizarre and bordered on impossible. Scientists found a supermassive black hole existing almost entirely alone in space, with barely any galaxy surrounding it at all, a cosmic monster without a home. Roberto Maiolino, a distinguished astrophysicist working at Cambridge University in England, led the international team that carefully characterized this extraordinary object. When they first examined the incoming data from Webb, they genuinely thought something must be wrong with their analysis. Perhaps an instrument error, perhaps a calibration problem, perhaps some foreground contamination confusing the measurements. Black holes are supposed to live inside galaxies, surrounded by billions of stars. They are supposed to grow alongside massive stellar populations, feeding them material over cosmic time. Finding one floating nearly naked through the void of intergalactic space seemed flatly impossible, according to every existing model of cosmic structure formation. But the observations held up through repeated analysis, using multiple independent methods. Every test confirmed the original finding. This black hole contains roughly 50 million stellar masses concentrated in its event horizon, yet around it there is almost nothing visible, a few faint wisps of gas barely detectable even with Webb's extraordinary sensitivity. Perhaps some extremely faint stellar light at the very edge of detection, but no significant galaxy anywhere nearby. The researchers described it publicly as completely off the scale of anything previously observed. Nothing whatsoever in any standard model of galaxy formation predicts such a strange and lonely object should exist. If black holes truly grow from stellar seeds forming inside galaxies, as the traditional theory insists, there should always be a substantial galaxy present surrounding any supermassive black hole. The stars and the central black hole should form together and grow together over cosmic time in a closely linked partnership. You cannot have one without the other under this framework. This astonishing discovery breaks that fundamental rule entirely. The black hole definitely exists based on its gravitational and radiation signatures, but the expected galaxy simply does not exist around it. Several alternative explanations were immediately proposed by theorists struggling to understand the observation. Maybe the galaxy is actually there but simply too faint for even Webb to detect at such extreme distances. Maybe this particular black hole was violently ejected from its original home galaxy through some catastrophic gravitational interaction involving multiple black holes. Maybe we happen to be catching this particular system at some unusual transitional moment in its evolution. But the most intriguing and revolutionary possibility is that this black hole never had a parent galaxy in the first place. Perhaps it formed through direct collapse of a primordial gas cloud that simply never accumulated enough additional material to build any significant stellar population around itself. The black hole ate most of the available gas in its vicinity before those atoms could ever cool down and condense into stars. It consumed its own potential galaxy before that galaxy could be born. This interpretation would make it the purest example yet discovered of a direct collapse black hole. A heavy seed that formed extremely early in cosmic history, consumed everything within reach, and then sat quietly in the darkness with nothing left to eat and no stars to mark its location. The gas surrounding this lonely object provided yet another crucial clue supporting this interpretation. Spectroscopic analysis of the faint gas wisps revealed almost no heavy elements whatsoever. The oxygen abundance measures less than 1% of what we observe in modern galaxies that have experienced billions of years of stellar evolution. This gas is nearly pristine, almost completely unchanged from the original primordial hydrogen and helium that filled the universe shortly after the Big Bang. Heavy elements like carbon, oxygen, and iron are forged exclusively inside stars and scattered across space when those stars die in supernova explosions. If this object genuinely lacks heavy elements in its vicinity, that means very few stars have ever lived and died anywhere nearby throughout cosmic history. The black hole formed and grew without requiring stellar evolution to proceed first. Stephen Hawking proposed back in 1971 that black holes could form directly from density fluctuations in the early universe without needing any stellar precursor at all. This naked black hole, floating alone through space, might be powerful evidence that Hawking was right all along about the primordial universe. While previous discoveries strongly hinted at direct collapse happening somewhere in cosmic history, another remarkable finding may have provided something even more extraordinary. Astronomers might have actually caught the direct collapse process happening in real time, a black hole being born without any stars involved. The object earning all this attention is nicknamed the Infinity Galaxy because its unusual shape closely resembles the mathematical infinity symbol. Two bright red nuclei, connected by streaming rivers of stars and glowing gas, forming a distinct sideways figure 8 pattern visible in Webb's detailed images. Peter van Dokkum, a prominent astronomer working at Yale University, first discovered this peculiar object while carefully examining mountains of data from one of Webb's largest and most ambitious observing programs. The survey had captured images of over 1 million galaxies, spanning cosmic time from the present day back to the earliest epochs. The Infinity Galaxy immediately stood out from the crowd because of its bizarre configuration. The unusual double-lobed shape strongly suggested a violent head-on collision between two separate disk galaxies that smashed together at tremendous relative velocity. The catastrophic impact created expanding ring structures around each surviving nucleus and sent powerful shock waves propagating through all the gas caught between them. But the truly strange and unexpected part was what Van Dokkum found lurking in the middle of the chaos. Sitting exactly between the two galactic nuclei, suspended in a vast cloud of shocked and heated gas, was an actively feeding supermassive black hole, not located inside either colliding galaxy where black holes normally reside, floating in the space between them where no black hole should exist. This configuration completely defied all expectations based on standard physics. Supermassive black holes always live at the gravitational centers of their host galaxies. They do not float freely in the empty spaces between colliding systems. When two galaxies eventually merge completely, their respective central black holes will sink toward the combined center through a process called dynamical friction and eventually combine. But that sinking process requires hundreds of millions of years to complete. The Infinity Galaxy system is far too young for any black hole merger to have occurred yet. The collision obviously happened recently in cosmic terms. Van Dockum and his research team proposed something genuinely radical to explain this impossible configuration. The black hole floating between the two nuclei did not migrate there from either parent galaxy. It did not exist before the collision began. It formed right there in the aftermath of the violent galactic collision. When the two galaxies smashed together at hundreds of miles per second, the gas trapped between them experienced extreme compression and heating beyond anything that normally occurs in the universe. The collision created exactly the physical environment that theoretical models predicted would enable direct collapse: extremely dense and turbulent gas, temperatures high enough to prevent molecular cooling and subsequent fragmentation. A massive reservoir of raw material primed to fall inward rapidly as a single coherent unit rather than fragmenting into countless stars. Under precisely these conditions, a supermassive star could have formed almost instantly and immediately collapsed into a black hole. The entire dramatic process, from initial gas compression to final black hole formation, might have taken less than 1 million years. An eye blink in cosmic terms. We may actually be seeing this newborn monster just moments after its birth, still completely surrounded by the very gas cloud that created it, still feeding on its placental material. If this interpretation survives further scrutiny and testing, the Infinity Galaxy represents the first direct observation in human history of a direct collapse black hole actually forming. Not an ancient relic from billions of years ago. A relatively recent event captured by Webb's infrared eyes almost in real time. This suggests direct collapse might not be limited exclusively to the primordial cosmos when the universe was young. It could potentially happen whenever the right extreme conditions arise through galactic collisions. Even today, even in our relatively nearby cosmic neighborhood, even now, the fundamental physics underlying direct collapse depends entirely on one absolutely crucial factor. The collapsing gas must stay hot throughout the entire process. If the gas manages to cool down efficiently, it will inevitably fragment into countless small pieces that each become individual stars. If the gas somehow stays warm and maintains high internal pressure, it can collapse smoothly as a single massive unified object heading straight toward black hole formation. Temperature controls absolutely everything in the behavior of collapsing gas clouds. Hot gas possesses high internal pressure because the individual particles are moving rapidly in random directions. This pressure resists compression and keeps the cloud unified against its own gravity. Cold gas possesses low internal pressure because the particles are moving slowly. Without sufficient pressure support, cold gas clumps together easily under gravity's relentless squeeze, fragmenting into countless dense knots. In a normal star-forming molecular cloud found throughout the modern universe, hydrogen molecules act like countless tiny refrigerators working together. They efficiently absorb thermal energy from random collisions with other particles, then radiate that captured energy away as infrared photons escaping into the void of space. This continuous cooling process allows the cloud to gradually contract further and further. As it contracts, it fragments into smaller pieces. Each piece continues contracting and cooling independently until stellar cores finally form and ignite nuclear fusion. Direct collapse requires completely disabling these molecular refrigerators before they can fragment the cloud. Without hydrogen molecules present in the gas, the cloud simply cannot cool efficiently through this pathway. The only remaining cooling mechanisms involve individual atoms rather than molecules, and atomic cooling is dramatically less effective at removing thermal energy. The gas stays hot enough to maintain pressure support and collapse smoothly as a single unified mass rather than fragmenting into stellar building blocks. Several different physical mechanisms can either destroy existing hydrogen molecules or prevent them from forming in the first place. Intense ultraviolet radiation represents the most thoroughly studied pathway to molecular destruction. Photons in a specific wavelength range, called the Lyman-Werner band, carry exactly the right amount of energy to break apart hydrogen molecules through a quantum process called photodissociation. If the ultraviolet radiation bathing a gas cloud is sufficiently intense, molecules get destroyed faster than random collisions can create new ones. The gas stays atomic and cannot cool efficiently. The early universe naturally provided abundant sources of this sterilizing radiation. Young galaxies with hot, massive stars emitted enormous floods of ultraviolet light in all directions. Any gas cloud sitting within range of this intense radiation bath would have its molecular hydrogen continuously stripped away and destroyed. Extreme turbulence provides another pathway to keeping gas hot during collapse. When gas moves chaotically at very high speeds with constant random motions, the kinetic energy of that turbulent motion continuously converts into thermal energy through shocks and compression events happening throughout the cloud. A sufficiently turbulent cloud generates its own internal heating through this mechanical process, counteracting and overwhelming any cooling mechanisms trying to remove energy. The catastrophic collision observed in the Infinity Galaxy created exactly this kind of extreme turbulent environment. Two entire galaxies smashing together at relative velocities of hundreds of miles per second generated absolutely tremendous turbulence in all the gas caught between them. Powerful shockwaves continuously heated the material. Chaotic random motions kept injecting fresh energy faster than any cooling process could possibly radiate it away into space. Under these extreme and violent conditions, even a very massive gas cloud physically cannot fragment into stars. It collapses instead as a single coherent unit, growing steadily denser and denser until absolutely nothing can halt the final catastrophic plunge into black hole formation. No stellar intermediate stage ever occurs because the gas never cooled enough to fragment. Sophisticated computer simulations have modeled this entire process in extraordinary detail using the most powerful supercomputers available. They consistently confirm that under the right initial conditions, clouds containing between 100,000 and 1 million stellar masses can collapse into supermassive stars within just a few 100,000 years. These supermassive stars burn at extreme temperatures, but only briefly. Then they collapse entirely into black holes without exploding outward in supernovae. The simulation predictions match remarkably well with what Webb has actually observed in the distant universe. Theoretical predictions and real observations are converging toward the same revolutionary conclusion. Direct collapse is real. It happened, and it may explain the most mysterious objects ever discovered in the cosmos. The remarkable idea of primordial black holes forming in the first moments of existence is completely inseparable from the scientific legacy of Stephen Hawking. His groundbreaking theoretical work in the early 1970s laid the mathematical foundations for understanding how such extraordinary objects could possibly exist. Hawking was powerfully drawn to studying black holes because they represented the ultimate test of physical theories at their most extreme limits. These objects combine general relativity, which describes gravity and the large-scale curvature of space-time, together with quantum mechanics, which governs the bizarre behavior of particles at the smallest possible scales. At the event horizon of any black hole, both of these fundamental theories become important simultaneously and must somehow work together consistently. In 1971, Hawking published a revolutionary scientific paper exploring what kinds of black holes might have formed naturally in the extremely early universe long before any stars existed. He demonstrated through careful mathematical analysis that the extreme densities present in the cosmos just moments after the Big Bang could have created black holes through direct gravitational collapse without requiring any stellar precursor whatsoever. No massive stars needed to form first. No supernovae needed to occur. Just the pure force of gravity acting on random density fluctuations in the primordial soup of energy and matter. The mass of any primordial black hole formed through this process would depend entirely on exactly when during the early universe it happened to collapse. Hawking calculated that black holes forming around 1 microsecond after the Big Bang would end up with masses comparable to typical asteroids in our solar system. Those forming slightly later, at around 1 second, would have masses rivaling entire mountains. Those forming at approximately 1 minute after the beginning could match the mass of planets. But crucially for explaining what Webb has discovered, black holes, forming anywhere from a few seconds to a few minutes after the Big Bang, could have ended up with masses ranging from thousands to potentially millions of stellar masses. These would represent absolutely perfect seeds for growing the supermassive black holes we now observe in the centers of galaxies throughout the universe. 3 years after his initial primordial black hole paper, Hawking made what would become his single most famous scientific discovery. He demonstrated through an elegant combination of quantum mechanics and general relativity that black holes are not actually completely black, as everyone had previously assumed. Quantum effects occurring near the event horizon cause black holes to emit faint radiation continuously, a phenomenon now universally called Hawking radiation in his honor. Over immense timescales far longer than the current age of the universe for large black holes, this gradual energy loss causes black holes to slowly shrink and eventually evaporate completely into pure radiation. This profound prediction fundamentally transformed black hole physics and connected these gravitational monsters to the deepest unsolved questions in theoretical physics regarding how gravity and quantum mechanics ultimately unite. Hawking spent many subsequent years actively advocating for primordial black holes as important cosmological objects, deserving serious scientific attention. He clearly recognized their potential power to solve multiple cosmic puzzles simultaneously. They could naturally seed supermassive black holes without requiring stellar precursors. They could potentially constitute the mysterious dark matter pervading the universe. They could produce gravitational wave signals detectable by future observatories. For decades after his proposals, the broader scientific community largely set aside the primordial black hole idea as an interesting theoretical curiosity lacking observational support. Other explanations seemed simpler and more grounded in known physics. The hypothesis gathered dust in textbooks. Then Webb launched and started finding supermassive black holes existing in the earliest observable epoch of cosmic history. Objects that simply could not exist under any standard formation theory involving stars. And suddenly, Stephen Hawking's 50-year-old prediction looked remarkably prescient, perhaps even prophetic. The simplest explanation for these otherwise impossible ancient objects might just be that they formed at the very beginning of time itself, exactly as Hawking had suggested decades earlier, when few took the idea seriously. If this interpretation proves correct, it means black holes were genuinely present in the cosmos before the first stars ever ignited, before the first atoms finished forming, before anything else we recognize existed anywhere. And that revolutionary conclusion changes absolutely everything about how we understand cosmic history and our own origins. The formation of primordial black holes requires understanding the very first moments after the Big Bang. This is a realm where normal human intuition fails completely, and only mathematics can guide us through the strangeness. At 1/1,000,000,000th of a second after the Big Bang, the entire observable universe that today spans nearly 100 billion light-years was compressed into a region smaller than our solar system. All the matter and energy that would eventually become hundreds of billions of galaxies containing hundreds of billions of stars, each was squeezed into a space that modern spacecraft could cross in mere hours. The temperature at this moment exceeded trillions of degrees, far hotter than the center of any star, far hotter than any supernova explosion. Matter existed in a bizarre state called quark-gluon plasma, where even protons and neutrons could not hold themselves together. The fundamental building blocks of atoms were broken apart into their constituent quarks, swimming freely through a sea of pure energy. Space itself was expanding at absolutely tremendous rates, stretching and cooling this primordial fireball with every passing microsecond. This unimaginably early universe was almost perfectly smooth and uniform throughout its volume, but crucially not quite perfectly smooth. Tiny quantum fluctuations, occurring at scales far smaller than atoms, created slight random variations in density from place to place throughout the primordial plasma. Some microscopic regions ended up a tiny fraction of a percent denser than the average. Other regions ended up a tiny fraction of a percent less dense. These variations were incredibly small in magnitude, but they were absolutely everywhere. In the vast majority of regions throughout the early universe, these primordial density fluctuations were far too subtle to matter in any immediate sense. The relentless expansion of space diluted them and stretched them out before gravity could amplify them into anything significant. These weak fluctuations would eventually become the seeds of galaxies and galaxy clusters, but only after billions of years of patient gravitational growth during which matter slowly accumulated into the cosmic web we observe today. But in certain rare exceptional regions, scattered randomly throughout the early universe, the initial fluctuations were dramatically larger than average, much larger. Statistical outliers in the random quantum noise. These represented extreme density peaks where matter concentrated so strongly that gravity overwhelmed the expansion of space itself in that local region. While the rest of the universe continued expanding outward and cooling down, these overdense pockets began collapsing inward under their own tremendous gravitational self-attraction. In these exceptional locations, matter fell inward catastrophically while everything else moved outward. Within merely a fraction of a second after the fluctuation formed, the collapsing pocket reached critical density where nothing could escape. An event horizon formed around the infalling matter. A black hole was born before atoms even existed, before light could travel freely through space, before the universe was even 1 second old. The mass of each primordial black hole depended entirely on how much matter happened to be contained within its particular collapsing region at the moment of formation. Earlier formation, when the universe was denser but smaller, meant smaller black holes. Later formation, when densities had dropped but volumes were larger, meant bigger black holes. Theoretical calculations suggest primordial black holes, forming between 1 microsecond and 1 second after the Big Bang, could span an enormous mass range from roughly 100 grams up to 100,000 stellar masses. The exact distribution across this range depends sensitively on the detailed physics of cosmic inflation and the precise statistical properties of the primordial density fluctuations generated during that epoch. If even a small fraction of the early universe happened to form primordial black holes with masses exceeding 1,000 stellar masses, these objects would have served as absolutely perfect seeds for supermassive black hole growth. They would have been scattered throughout all of space from the very beginning, ready and waiting to sink into the gravitational centers of forming galaxies billions of years later and begin their journey toward becoming the billion stellar mass monsters we observe today. No stars were required for this process. No special gas cloud conditions needed to occur, just gravity acting directly on primordial density fluctuations during the first second of cosmic history. This remarkable theory remained speculative for decades after Hawking first proposed it. But Webb's revolutionary discoveries have brought primordial black holes back into serious mainstream scientific discussion as perhaps the best explanation for what we observe. The implications extend far beyond black holes themselves. If density fluctuations during the first second created these massive objects, it reveals something fundamental about the physics of the Big Bang itself and the quantum processes that shaped everything. Among all the remarkable discoveries that Webb has delivered during its first years of operation, one particular galaxy stands out for how dramatically and inexplicably it violates every expectation from standard cosmic evolution models. The supermassive black hole at its center is growing at a rate that approaches the physically impossible. This extraordinary galaxy was identified through an ambitious survey program that uses a phenomenon called gravitational lensing to see deeper into the universe than would otherwise be possible. Massive galaxy clusters containing trillions of stellar masses act like enormous cosmic magnifying glasses, bending and amplifying light from much more distant objects located behind them. This natural magnification effect allows astronomers to study extremely faint and faraway galaxies in unprecedented detail that would be impossible without nature's assistance. The galaxy in question sits at such an extreme distance that we observe it as it appeared just 570 million years after the Big Bang. This makes it one of the most distant galaxies ever discovered, with a confirmed actively feeding supermassive black hole at its center. We are seeing it as it was over 13 billion years ago, when the universe was barely 4% of its current age. When researchers carefully analyzed the spectrum of light from this ancient galaxy, they found unmistakable signatures of active black hole accretion occurring at tremendous rates. Gas in the immediate vicinity of the central black hole was highly ionized, completely stripped of its electrons by the intense radiation pouring out from the accretion disk. The gas was also rotating extremely rapidly around the center, swirling in a tight orbit that betrayed the presence of an enormous hidden mass concentration. These spectral features are unmistakable fingerprints of a supermassive black hole actively pulling in surrounding material and converting it into energy. The estimated mass of this voracious black hole is approximately 100 million stellar masses based on the dynamics of the surrounding gas. This measurement alone already severely strains standard formation models that rely on gradual growth from small stellar seeds. But the truly remarkable and disturbing finding concerned the relationship between this black hole and the galaxy hosting it. In galaxies throughout the nearby universe that astronomers have studied in great detail over decades, black hole mass and total galactic stellar mass follow a remarkably tight and consistent correlation. Larger galaxies systematically host larger central black holes with a typical mass ratio of approximately 1 to 500. The black hole contains roughly 0.2% of the total stellar mass in its host galaxy. This ancient galaxy violates that well-established relationship in spectacular fashion. Its central black hole is dramatically overmassive compared to the surrounding stellar population. The ratio sits closer to 1 to 10 rather than 1 to 500. The black hole contains somewhere between 10 and 20% of all the stellar mass present in the entire galaxy. This extraordinary ratio means the black hole grew far faster than the galaxy surrounding it could possibly form stars. Or, alternatively, it means the black hole started out already massive before the galaxy even began assembling its stellar population. Either interpretation fundamentally challenges every standard picture of coordinated black hole and galaxy growth that astronomers have developed over the past several decades of careful study. The lead researcher on this discovery described the finding as truly remarkable and unprecedented. The black hole is growing extremely rapidly, far faster than any theoretical model predicted should be possible for a galaxy at this early cosmic time. More examples of these overmassive black holes keep appearing in Webb data with every new observing campaign and every new analysis of existing images. The early universe seems absolutely filled with supermassive black holes that somehow dramatically outpaced the growth of their host galaxies. These observations strongly suggest that black holes led the way during the earliest phases of cosmic evolution. The galaxies we see today followed behind, gradually catching up over billions of subsequent years. And the tight relationship we observe between black holes and galaxies in the modern universe took billions of years to finally establish itself through slow mutual regulation. The relationship between supermassive black holes and the galaxies containing them has puzzled astronomers for decades. Why do bigger galaxies consistently host bigger central black holes across the entire observable universe? What invisible connection links these two very different types of objects spanning scales from light years to hundreds of thousands of light years? The correlation observed in nearby well-studied galaxies is remarkably tight and consistent. Scientists have confirmed this relationship through detailed observations of hundreds of individual galaxies using multiple independent measurement techniques. If you measure a galaxy's total stellar mass by adding up all the light from all its stars, you can predict the mass of its central black hole with reasonable accuracy even without observing the black hole directly. Similarly, if you measure the velocities of stars orbiting in the galaxy's central bulge region, you can estimate the black hole mass from the dynamics alone. The relationship spans an enormous range, covering 5 orders of magnitude from the smallest galaxies with million stellar mass black holes up to the largest giants harboring monsters of 10 billion stellar masses. This remarkably tight correlation strongly suggests that black holes and their host galaxies grow together over cosmic time through some form of mutual regulation. They influence each other continuously through feedback processes that connect their fates. When a central black hole feeds actively on surrounding gas, it releases absolutely enormous amounts of energy in the form of radiation and powerful outflows. This energy heats the surrounding gas throughout the galaxy and can suppress further star formation by preventing gas from cooling and condensing. When vigorous star formation occurs throughout a galaxy, it produces winds and supernova explosions that can drive gas toward the center, where it eventually falls onto the black hole and feeds its growth. The two components appear to regulate each other's growth through this back and forth exchange of matter and energy. This mutual feedback naturally maintains the observed mass ratio over billions of years of cosmic evolution. But Webb's revolutionary discoveries strongly suggest this balanced relationship did not always exist throughout cosmic history. In the early universe, during the first billion years after the Big Bang, black holes appear to have grown dramatically faster than their host galaxies could form stars. They achieved supermassive status, containing hundreds of millions of stellar masses before the surrounding stellar populations could accumulate even a fraction of their eventual final mass. Several different mechanisms could potentially explain this striking early imbalance. If black holes formed through direct collapse or emerged as primordial seeds from the first second of cosmic history, they would have started out already massive before any galaxy formation occurred at all. The surrounding galaxy would then need to slowly grow and accumulate around an already gigantic central black hole. This process of catching up would require billions of years of steady star formation to approach the final balanced ratio. Alternatively, feedback effects might have operated very differently during the extreme conditions of the early universe compared to today. Extraordinarily dense primordial gas could have funneled onto young black holes with much greater efficiency, feeding them faster than normal accretion physics would predict for later epochs. Or the intense radiation from rapidly growing early black holes might have suppressed star formation more effectively than similar radiation does today, keeping host galaxies artificially small while their central black holes grew to enormous sizes. Computer simulations exploring both scenarios consistently show that overmassive early black holes naturally evolve toward the locally observed balanced relationship over cosmic time. Host galaxies keep steadily forming new stars and growing larger through mergers and gas accretion. Black holes gradually slow their feeding rates as surrounding gas supplies deplete. Eventually, over billions of years, the ratio converges toward what we observe in nearby mature galaxies. If this interpretation proves correct, the overmassive black holes Webb is discovering represent a temporary transient phase in cosmic evolution that every galaxy passed through early in its history. Black holes led the way forward, forming first, growing fast, shaping their environments. Galaxies followed behind over billions of years, gradually building up their stellar populations until the mature relationship finally established itself. We are witnessing the universe during its awkward teenage years, before the balanced adult relationship between black holes and galaxies finished developing. Once a massive black hole seed forms in the early universe through whatever pathway created it, that seed immediately faces a feast beyond anything imaginable in the modern cosmos. Surrounded by extraordinarily dense clouds of pristine primordial gas, It can feed voraciously and continuously for tens of millions of years without interruption. The early universe was a far denser environment than anything existing in the cosmos today. This fact has been confirmed through multiple independent lines of observational evidence and theoretical modeling. Galaxies were packed much closer together during those early epochs when the universe was physically smaller. Intergalactic gas clouds were dramatically thicker and more massive than anything found in modern cosmic voids. The space between forming structures contained vastly more raw material available for accretion than the sparse empty regions separating mature galaxies today. Everything was closer, everything was denser, everything was available for consumption. A young black hole finding itself embedded in this primordial environment would have discovered itself literally swimming in potential fuel. Gas flowed toward it from every direction simultaneously, drawn inexorably inward by its intense gravitational pull. Without the competing gravity of a fully formed massive galaxy to hold material in stable orbits away from the center, the black hole could claim an enormous reservoir of gas for itself. As gas fell inward toward the event horizon, it naturally formed a rapidly spinning accretion disk around the black hole. Tremendous friction within this disk heated the infalling material to temperatures exceeding millions of degrees. The inner regions of the disk glowed brilliantly across multiple wavelengths, producing enormous amounts of X-rays and ultraviolet light visible across cosmic distances. Energy poured outward from the black hole's vicinity, illuminating the surrounding universe with the intensity of entire galaxies. This is precisely what astronomers observe when they detect the mysterious little red dots in Webb's deep images of the early universe. Young supermassive black holes wrapped in thick cocoons of infalling gas. Their brilliant accretion disk light filtered through intervening dust and dramatically stretched by cosmic expansion until it appears as infrared radiation detectable by Webb's sensitive instruments. Hidden monsters feeding in the primordial darkness. Some of these early black holes appear to be feeding at rates approaching the theoretical Eddington limit, representing the maximum sustainable accretion rate. Others might even temporarily exceed this limit during brief, intense bursts of super-Eddington accretion when gas pours in faster than radiation pressure can push it away. The growth rates, implied by Webb's observations of these objects, are genuinely staggering when you calculate the implications. A black hole that somehow reached 100 million stellar masses by just 500 million years after the Big Bang must have been gaining mass almost continuously throughout that entire period. Even brief pauses in active feeding lasting more than a few million years would have made the final observed mass mathematically unreachable within the available cosmic time. This constant, voracious feeding had significant consequences extending far beyond the black hole itself. Intense radiation pouring from accretion disks ionized hydrogen gas throughout enormous volumes, spanning millions of light years in every direction around each feeding black hole. This radiation heated the intergalactic medium to high temperatures, actively preventing new galaxies from forming in nearby regions where gas could not cool and collapse. Powerful relativistic outflows swept surrounding gas completely out of the black hole's gravitational sphere of influence. These feedback effects eventually brought the feeding frenzy to an end through self-regulation. As each black hole consumed all nearby available gas and expelled more distant gas through radiation pressure and outflows, its fuel supply inevitably dwindled. The brilliant quasar phase gradually faded to dimness. The black hole settled into a much quieter existence, waiting potentially billions of years for its host galaxy to deliver fresh material through subsequent mergers or slow gas inflows from the intergalactic medium. This cycle of feast, followed by extended famine, repeated across the entire early universe wherever massive black holes existed. But the most intense and dramatic feeding happened extremely early in cosmic history, when the universe was still young and extraordinarily dense. When black hole seeds could grow almost without any limit imposed by gas availability, that primordial feeding frenzy shaped the cosmos we inhabit today. The accumulating discoveries from Webb and other observatories keep pointing toward a stunning and revolutionary possibility that inverts everything astronomers believed for decades. Supermassive black holes might have been among the very first large structures to exist anywhere in the universe, present and active before the first stars ever ignited their nuclear fires. This radical idea completely inverts the traditional story of cosmic evolution that has dominated astronomy textbooks for generations. The standard narrative always placed stars firmly first in the sequence of structure formation. Gravity slowly pulled primordial gas together over hundreds of millions of years, forming increasingly dense clumps that eventually ignited nuclear fusion and became the first stars. These population 3 stars lived brief, violent lives, burning through their hydrogen fuel rapidly before exploding in supernovae and leaving behind black hole remnants. Those stellar mass black holes then found each other, merged together, and gradually grew larger over billions of years by consuming surrounding gas. Galaxies slowly assembled around these growing black holes through countless mergers and accretion events. The entire traditional process required billions of years to build complexity step by step, from small beginnings to the supermassive monsters we observe today. But Webb's observations are now painting a dramatically different picture of early cosmic history. The earliest confirmed supermassive black holes appear completely fully formed in the data, already containing hundreds of millions of stellar masses, already actively feeding on surrounding gas at tremendous rates, already dominating the energy output of their host systems. The small, young galaxies surrounding them appear underdeveloped and understaffed compared to what standard models predict should exist around such massive central objects. The expected multiple generations of stellar evolution that should have preceded supermassive black hole formation simply have not occurred based on the chemical evidence. The gas around some early black holes remains nearly pristine, lacking the heavy elements that dying stars would have scattered everywhere. If supermassive black holes genuinely came first and existed before significant stellar populations formed, they would have fundamentally shaped absolutely everything that followed throughout cosmic history. Their immense gravity would have drawn gas inward from vast distances, creating the dense central concentrations where stars eventually ignited. Their intense radiation would have ionized surrounding gas throughout enormous volumes, influencing the detailed chemistry and cooling rates of later star formation. Their powerful feedback through outflows and radiation pressure would have regulated exactly how fast surrounding galaxies could grow and form new stellar generations. The black hole would not be merely a passive product of galactic evolution in this picture. It would be an active driver and architect of that evolution from the very beginning. Several independent lines of observational evidence now support this revolutionary black hole first picture. The overmassive black holes, appearing in nearly every early galaxy Webb, has studied suggest black hole growth systematically outpaced stellar growth during the first billion years. The naked black hole floating without any significant galaxy demonstrates that supermassive black holes can exist completely independently of stellar populations. The nearly pristine chemical composition of gas around some early black holes indicates minimal prior stellar enrichment in their vicinities. And then there is the simple, unavoidable mathematics of cosmic timing itself. The universe was only a few 100 million years old when these supermassive black holes were already observed sitting in place. The first stellar generation of population. 3 stars had barely begun forming anywhere when these monsters already existed. There simply was not enough elapsed cosmic time for multiple generations of stars to form, evolve, die, leave black hole remnants, and have those remnants merge repeatedly into supermassive objects. The math overwhelmingly favors non-stellar formation channels that created massive black holes directly, either through direct collapse of primordial gas clouds under special conditions, or through primordial formation from density fluctuations during the very first second after the Big Bang. Both of these pathways create massive black holes before stars contribute anything whatsoever to the process. Some researchers have begun calling this emerging understanding the black hole first paradigm. It represents a fundamental shift in how we understand the assembly of all cosmic structure throughout the universe, including the structure that eventually produced us. The James Webb Space Telescope continues pushing deeper into cosmic history with every new observation, reaching epochs so ancient that they should have been completely dark according to every standard model of universal evolution. And yet Webb keeps finding sources of light shining where absolutely nothing should have existed to produce illumination. In 2025, astronomers announced detecting extremely faint blue sources at almost inconceivable distances. These detections correspond to cosmic ages of roughly 100 to 200 million years after the Big Bang. This places them squarely within the period astronomers call the cosmic dark ages, the extended epoch after the hot primordial plasma finally cooled enough to become transparent, but before the first generation of stars managed to form and ignite. Absolutely nothing should have been shining anywhere in the universe during this dark era. Every theoretical model confirms this expectation. The cosmos at that time was filled with nothing but neutral hydrogen gas, slowly drifting and cooling and gradually condensing under the patient pull of gravity into increasingly dense structures. No stars had yet ignited anywhere because the gas had not yet concentrated enough to trigger nuclear fusion. No galaxies had assembled because there were no stars to compose them. The entire observable universe should have been utterly black in every direction, a vast dark void waiting for the first lights to eventually switch on. Yet Webb detected 9 distinct sources of ultraviolet light emerging from this supposedly completely dark period of cosmic history. 6 sources appeared at a distance corresponding to roughly 170 million years after the Big Bang. 3 more appeared even deeper at roughly 120 million years after creation. What could possibly have produced light during an era when nothing luminous should have existed anywhere? The research team carefully considered multiple alternative explanations before concluding the detections were genuine. Instrumental artifacts and calibration errors were systematically ruled out through exhaustive testing. Foreground contamination from closer, unrelated objects was evaluated and rejected through spectroscopic analysis. The sources genuinely appear to originate from the extreme depths of cosmic time during the supposedly dark ages. One compelling explanation for these impossible lights involves primordial black holes lurking in the darkness. If massive black holes truly existed in the early universe from the very first second, they would have continuously attracted surrounding gas toward themselves through gravity, even during the cosmic dark ages. As this gas fell inward toward each black hole's event horizon, it would have heated up through friction and compression. It would have glowed brightly across multiple wavelengths. Black holes could have served as cosmic lighthouses illuminating an otherwise completely dark universe. Their accretion disks shining brilliantly before any stars existed anywhere. This scenario fits remarkably well with the actual detected properties of these mysterious sources. The objects appear compact and blue in Webb's images, consistent with hot accretion disks surrounding massive central objects. Their brightness levels suggest substantial mass concentrations are present to power such luminous output. Their presence at such extremely early times completely rules out any formation pathway that requires prior stellar evolution. Alternative explanations involve more exotic and speculative physics. Perhaps the very first stars somehow formed much earlier than any current theoretical model predicts through unknown mechanisms. Perhaps some completely unknown physical process generated light directly in the primordial gas without requiring stars or black holes. Whatever the ultimate explanation proves to be, these detections dramatically push the boundaries of observable cosmic history backward in time. They strongly suggest the universe was not entirely dark during its supposed dark ages after all. Something was already happening out there in the void. Something was already shining before stars existed. Something was already structuring the cosmos. If that something turns out to be black holes, then these gravitational monsters were truly among the very first significant structures to exist anywhere in the universe, predating even the very first generation of stars by tens of millions of years. This discovery challenges our most fundamental assumptions about how the cosmos first lit up, and it suggests black holes played a far more important role in the earliest epoch of cosmic history than anyone imagined possible. As observational evidence continues accumulating from Webb and other telescopes, scientists are gradually reaching a nuanced and sophisticated conclusion about how supermassive black holes came to exist. There almost certainly was not one single exclusive pathway to creating these cosmic giants. Multiple different formation mechanisms likely operated simultaneously throughout the early universe, each contributing black holes to the population we observe today. The traditional light seed pathway involving stellar collapse definitely happened and continues happening throughout the cosmos. We directly observe stellar mass black holes forming today when sufficiently massive stars exhaust their nuclear fuel and collapse. We detect gravitational waves rippling through space-time when pairs of stellar black holes spiral together and merge. The physics governing this process is thoroughly understood and clearly produces black holes in the mass range, spanning a few to perhaps 100 stellar masses. Some fraction of these light seeds undoubtedly did grow significantly over cosmic time through steady accretion of surrounding gas and occasional mergers with other black holes. In particularly dense galactic environments where abundant gas flows continuously toward the center, these seeds could have reached masses of millions of stellar masses over billions of patient years. This traditional pathway certainly contributes black holes to the supermassive population we observe throughout the modern universe. But it demonstrably cannot explain the most massive objects appearing earliest in cosmic history when insufficient time had elapsed for such gradual growth. Direct collapse from primordial gas clouds also appears to have genuinely occurred based on Webb's discoveries. The overmassive black holes Webb keeps finding in early galaxies, the naked black hole floating alone without any surrounding stellar population, and the possible ongoing direct collapse event witnessed in the Infinity Galaxy all point convincingly toward this alternative mechanism. Under the right specific conditions where intense ultraviolet radiation or extreme turbulence prevented gas from cooling and fragmenting, massive primordial clouds skipped the entire star formation phase and collapsed directly into heavy black hole seeds. These seeds emerged containing tens of thousands to perhaps 100,000 stellar masses from a single rapid collapse event. These heavy seeds possessed an enormous growth advantage over light stellar seeds. Starting already massive, they required far less subsequent growth to reach the supermassive regime we observe. Primordial black holes originating from density fluctuations in the first second after the Big Bang might have contributed additional seeds as well. If random quantum fluctuations during cosmic inflation occasionally produced regions dense enough to collapse directly into black holes before atoms even formed, these primordial objects would have provided instant ready-made seeds scattered throughout the entire universe from the very beginning. No waiting required for stars to form and die first. No special gas cloud conditions needed. Just gravity acting on primordial density fluctuations during the first moments of time. Each of these different pathways probably dominated black hole formation in different cosmic environments and at different epochs throughout universal history. Light seeds from stellar collapse might have been most important during later cosmic epochs after billions of years allowed sufficient stellar evolution to proceed. Direct collapse from gas clouds might have been most common in dense, highly irradiated regions near the first actively star-forming galaxies. Primordial black holes might have seeded the very first structures before any other formation mechanism could even begin operating. The relative importance of each pathway remains genuinely uncertain and actively debated. Distinguishing observationally between a direct collapse black hole and a primordial black hole proves extremely difficult because both produce remarkably similar outcomes. Both pathways yield massive black holes existing earlier than any stellar formation channel permits. Future observations using different techniques may eventually help separate these contributions. Advanced gravitational wave detectors could identify distinct populations of merging black holes with masses and merger rates consistent with primordial origins. Deeper Webb surveys could discover additional examples of direct collapse candidates caught in the act of forming. Statistical analysis of black hole masses versus host galaxy properties across cosmic time could reveal which pathways dominated at different epochs. For now, the evidence supports a diverse, multi-channel origin story for supermassive black holes. The universe apparently found several different ways to create its most extreme and powerful objects. The revolutionary discovery that supermassive black holes may have formed before their host galaxies ever assembled forces astronomers to completely rethink the entire history of cosmic structure formation from the very beginning. In the traditional theoretical picture that dominated astronomy for decades, galaxies always formed first in the sequence of structure assembly. Dark matter halos collapsed under their own gravity during the first few 100 million years, pulling ordinary visible matter inward into their gravitational centers. This gas cooled through radiation, condensed into increasingly dense clumps, and eventually formed the first stars. Over subsequent billions of years, stellar populations grew larger through continued star formation and mergers between smaller systems. Galactic structures gradually took their familiar shapes. Spiral arms emerged. Elliptical bulges formed. Complex chemical evolution enriched the gas with heavy elements. Black holes in this traditional picture were merely passengers along for the ride during galactic evolution. They formed from dead stellar remnants and grew slowly alongside their host galaxies without fundamentally driving the process. The emerging new picture, painted by Webb's observations, is fundamentally different in almost every respect. Black holes may have been active drivers of galactic evolution rather than passive passengers carried along by other processes. They formed early through non-stellar pathways like direct collapse or primordial formation. They existed and began influencing their surroundings before significant stellar populations had time to assemble. This reversal of the traditional sequence has profound implications for understanding how all galaxies throughout the universe came to exist in their current forms. A massive black hole sitting at the gravitational center of a forming galaxy would powerfully influence absolutely everything happening around it. Its immense gravity would attract gas from distances spanning millions of light years, channeling material toward the galactic center where it could feed the growing black hole or form new stars in dense concentrations. Its intense radiation during active feeding phases would heat and ionize surrounding gas throughout enormous volumes, fundamentally affecting how efficiently that gas could cool and form stars elsewhere in the galaxy. Its feedback through powerful outflows would regulate the overall growth rate of the entire host galaxy by periodically expelling gas that would otherwise form stars. Sophisticated computer simulations that incorporate early massive black holes as initial conditions produce galaxies that look noticeably different from those grown in simulations without such seeds. Stellar populations become more centrally concentrated around the massive gravitational anchor. Star formation history becomes more episodic, with bursts of activity followed by quiet periods when feedback suppresses further growth. The relationship between black hole mass and total galaxy mass evolves dramatically over cosmic time rather than remaining fixed. These simulation predictions match remarkably well with what Webb actually observes in the real early universe. The overmassive black holes dominating small host galaxies, the compact concentrated stellar structures, the clear evidence of strong feedback affecting star formation rates. Theory and observation are converging toward the same revolutionary conclusion about how galaxies truly assembled. There are also profound implications extending to dark matter itself. Some researchers seriously propose that primordial black holes could themselves constitute the mysterious dark matter that outweighs ordinary visible matter throughout the universe by a ratio of 6:1. If sufficient numbers of primordial black holes formed during the first second after the Big Bang, they could collectively account for all the gravitational effects we attribute to dark matter without requiring any new exotic fundamental particles beyond the standard model. This idea remains controversial because observational constraints limit how much total mass could plausibly be locked up in primordial black holes across various mass ranges. But the possibility illustrates how deeply Webb's discoveries connect to fundamental unresolved questions in cosmology and particle physics. The role of black holes in shaping cosmic evolution is being completely rewritten by these observations. From minor supporting players emerging late during galactic history, they have become central starring characters appearing at the very beginning and influencing everything that followed. Understanding black hole formation and early growth is now absolutely essential to understanding how the universe itself came to look the way it does, including understanding how our own Milky Way galaxy formed around its central supermassive black hole over 13 billion years of cosmic history. Armed with revolutionary new understanding of how supermassive black holes might form, astronomers around the world are now actively hunting for additional examples of direct collapse black holes hiding in Webb's vast data archives and in new targeted observations. Every confirmed discovery helps further constrain the physics governing early black hole formation and tests competing theoretical models against reality. The search focuses on several specific observable signatures that direct collapse black holes should exhibit if the theory is correct. Direct collapse black holes should appear dramatically overmassive compared to their host galaxies, especially during the earliest cosmic epochs, when galaxies have not yet had time to catch up through star formation. They should exist preferentially in environments showing low metallicity, meaning few heavy elements are present because minimal stellar evolution has occurred to produce and scatter such elements. They should show clear spectroscopic evidence of rapid ongoing accretion as they consume surrounding gas at rates approaching or even exceeding theoretical limits. The mysterious little red dots that Webb continues discovering in deep survey images represent primary targets for this systematic hunt. These compact, distinctively red, extremely distant objects frequently harbor actively feeding supermassive black holes buried within small young galaxies. Detailed spectroscopic follow-up observations using Webb's powerful instruments can measure gas velocities orbiting the central mass, determine chemical compositions of surrounding material, and estimate black hole masses through dynamical modeling. Each measurement tests whether individual objects fit the predicted profile for direct collapse formation or require alternative explanations. The remarkable Infinity Galaxy, with its black hole apparently forming between two colliding nuclei, provides a completely different search strategy. If direct collapse can genuinely occur whenever galaxies collide under the right extreme conditions, astronomers should actively look for similar unusual configurations at various cosmic epochs throughout universal history. Interacting galaxy pairs showing supermassive black holes located between their respective nuclei, rather than inside them, could represent additional examples of collision-triggered direct collapse caught at various stages. Such systems would confirm that this formation pathway operates not just in the primordial universe, but continues occurring whenever appropriate conditions arise. Gravitational wave astronomy offers yet another completely independent avenue for hunting direct collapse black holes. When extremely massive black holes spiral together and merge, they produce powerful ripples in the fabric of space-time itself. Future space-based gravitational wave observatories like the planned LISA mission could detect mergers involving black holes in mass ranges specifically consistent with direct collapse heavy seeds rather than lighter stellar remnants. The statistical distribution of detected merger masses and rates would reveal how common heavy seed formation truly was during the early universe when most such objects formed. Indirect evidence can also powerfully constrain direct collapse rates, even without detecting individual objects directly. The total cumulative number of supermassive black holes observed across various cosmic epochs throughout universal history must be explained by some combination of formation pathways operating together. If direct collapse was common throughout the early universe, there should be many overmassive black holes in early small galaxies, and the total population should show distinctive statistical properties. If direct collapse was rare, the population should be dominated instead by objects grown more slowly from lighter stellar seeds through gradual accretion and mergers. Theorists continue simultaneously refining their predictive models as new observations arrive. Computer simulations of direct collapse have become increasingly sophisticated over recent years, incorporating ever more detailed gas physics, accurate radiative transfer of energy through collapsing clouds, realistic magnetic field effects, and complex turbulent dynamics. These simulations predict specific observable properties for direct collapse black holes that can be directly tested against Webb data as the catalogue of known early supermassive black holes continues growing. The next several years will almost certainly bring a flood of new discoveries advancing our understanding rapidly. Webb continues systematically observing the early universe and adding more confirmed little red dots and overmassive black holes to its growing scientific catalogue with every observing cycle. Other telescopes contribute essential complementary data at X-ray wavelengths, radio wavelengths, and through gravitational wave detections. The combined coordinated assault across multiple observational techniques will ultimately determine how supermassive black holes truly formed during cosmic dawn. And each new discovery brings humanity closer to understanding how the universe built its most powerful and extreme objects. Everything astronomers thought they understood about when major events happened during the history of the universe is now being dramatically revised based on Webb's revolutionary discoveries. The traditional neat timeline that filled astronomy textbooks for decades appears increasingly incomplete and possibly fundamentally wrong in important respects. The traditional timeline of cosmic evolution went something like this according to the old understanding. The Big Bang occurred 13.8 billion years ago, creating all matter and energy in an unimaginably hot, dense state. Space expanded and cooled over hundreds of thousands of years. Eventually, atoms formed for the first time when temperatures dropped enough for electrons to bind with nuclei. The cosmic dark ages began as the universe continued expanding in complete darkness. After roughly 150 million years, the first stars finally ignited from collapsing gas clouds. These first stellar generations lived and died, scattering heavy elements. First galaxies gradually assembled over hundreds of millions of years. Black holes formed from stellar remnants and slowly grew through patient accretion and mergers over billions of subsequent years. A neat, orderly progression from simple to complex. From small structures to large structures. From few objects to many objects. Each step following logically from the previous one, with plenty of time for gradual development. But Webb's observations strongly suggest this traditional timeline is wrong, or at least seriously incomplete. Supermassive black holes appeared far too early in cosmic history compared to what this timeline predicts. They were already far too massive, far too quickly. The neat, gradual progression simply did not happen as expected. Something was creating giant black holes containing hundreds of millions of stellar masses, while the universe was still in its earliest infancy, before enough time had passed for the standard slow growth scenario to work. The revised timeline emerging from Webb's data looks dramatically different. The Big Bang occurred, and within literally the first second, density fluctuations may have already created primordial black holes. Some of these primordial seeds were already massive enough to eventually anchor entire galaxies. Others may have been microscopic and contributed to dark matter or evaporated through Hawking radiation. During the subsequent cosmic dark ages before any stars existed, These black hole seeds began attracting surrounding primordial gas through their gravity. They started feeding and growing larger. They may have become the first sources of any light in the universe, their accretion disks glowing brilliantly while everything else remained dark. As gas accumulated around these pre-existing black holes, conditions eventually became favorable for the first stars to form in their vicinity. But critically, the black holes were already there waiting. They served as gravitational anchors around which the first proto-galaxies began assembling. Galaxies assembled around pre-existing black holes rather than creating black holes later as byproducts of stellar evolution. This represents a profound fundamental shift in understanding cosmic evolution. It means black holes are not merely the products of cosmic evolution that emerged late in the process. They are architects of cosmic evolution that shaped everything from the very beginning. They helped create the conditions that allowed stars and galaxies to form in the first place. The implications extend directly to our own existence as conscious beings capable of asking these questions. The Milky Way galaxy contains a supermassive black hole at its gravitational center that we call Sagittarius A star. If that black hole or its progenitor seed already existed before our galaxy assembled, it directly helped create the environment where our star eventually formed, where our planet eventually coalesced, where life eventually emerged and evolved. We exist in part because of black holes, in a much more direct and fundamental way than anyone previously imagined or suspected. Future observations, using Webb and other facilities, will continue refining this revolutionary new picture. But the direction of revision is already clear. Black holes were present at the very beginning of cosmic history. They influenced everything that happened afterward. The traditional timeline is being rewritten with black holes playing a central starring role from the first second onward. We began this journey with a simple but profound puzzle. Supermassive black holes existing in the early universe when they had no right to exist. Cosmic monsters fully grown and actively feeding when the universe was barely old enough to have formed the first stars. The standard story of cosmic evolution developed over decades of careful research simply could not explain what Webb was showing us. Now, after this journey through colliding galaxies, naked black holes, primordial gas clouds, and the first moments after creation itself, we have answers. Not complete final answers that resolve every question, but profound new insights that fundamentally reshape our understanding of where everything came from, including ourselves. Black holes did not patiently wait for stars to form and die before coming into existence. They formed through direct collapse of primordial gas clouds when specific conditions prevented normal star formation. They may have formed directly from density fluctuations during the very first second after the Big Bang. Primordial objects predating even the formation of atoms, predating light itself. They appeared extremely early in cosmic history. They grew extremely fast. They shaped the galaxies that assembled around them over billions of subsequent years. This revolutionary understanding changes the entire narrative of cosmic history that we tell ourselves about where the universe came from. The universe did not build itself gradually, from small, simple structures to large, complex structures in a neat, orderly bottom-up progression over billions of patient years. Instead, some of the most massive and powerful objects in existence formed first, right at the beginning. Before almost everything else, supermassive black holes became the gravitational seeds around which galaxies crystallized like frost forming on a cold window. Their immense gravity attracted gas from across vast cosmic distances. Their intense radiation during active feeding phases influenced the chemistry and temperature of surrounding material across millions of light years. Their powerful feedback through outflows regulated exactly how fast host galaxies could form new stars. They were architects of cosmic structure, active shapers of everything that followed, not merely passive byproducts of stellar evolution. The implications of this new understanding ripple outward in every direction across multiple scientific fields. Our understanding of galaxy formation must now incorporate early massive black holes as essential foundational ingredients rather than late additions. Our models attempting to explain dark matter must seriously account for possible contributions from primordial black holes formed in the first second. Our timeline of cosmic dawn must include black holes shining brightly before the first stars ever ignited. Stephen Hawking's theoretical speculations from over 50 years ago are finally being validated by real observations. Direct collapse theorists who worked in relative obscurity for decades, while mainstream astronomy ignored their ideas, are now seeing their predictions dramatically confirmed. Science progresses exactly this way. New observations force us to abandon comfortable old assumptions and embrace stranger truths about reality. The James Webb Space Telescope has given humanity eyes to see the early universe clearly for the first time in history. What we found out there in the distant past surprised everyone who looked. The early cosmos was far more violent than predicted, far more active than expected, far more structured far earlier than any model anticipated. Black holes were everywhere doing things they should not have been able to do. At the heart of all that early cosmic activity sat black holes, gravity wells of almost unimaginable power, born through processes we are only beginning to understand, shaping a universe that would eventually produce stars and planets and liquid water and organic chemistry and life and consciousness and curious beings who would look back across 13 billion years of cosmic history wondering how everything began. The search for answers continues with every new observation. More powerful telescopes, more sophisticated instruments, more discoveries waiting to be made. But one profound truth is already clear from what Webb has revealed. Black holes are not just endpoints of stellar evolution. They are fundamental to how the universe itself came to be. From the first second of existence to the present day, these invisible giants have been quietly pulling the strings of cosmic history, and we are only beginning to understand their true role in making everything possible, including making us possible.